And simply I'm writing if suppose A is the generator of a cyclic group, any cyclic group, suppose G, then so that inverse of A inverse denoted by A inverse, this denote the inverse of A is also a generator of the generator cyclic group. Cyclic group, that means if in a group all the elements can be expressed in terms of the other. Okay, that means you can express all the elements in terms of A, then it is said to be a cyclic group. So everybody know the modulo functions. I am just giving a question from the modulo, so that the group G is 1, 2, 3, 4, 5, 6, and modulo 7 with respect to multiplication. Modulo 7 with respect to multiplication is cyclic. And next we have a tail question, that is 7. How many generators are there? Okay, try to solve this 4 question. Today's question is from the cyclic group and the normal group. Okay, solve this 4. If G be a group and AB belongs to G, then prove that this. Simple question it is. So everybody try to solve it. I will ask one by one. So what is the idea to prove this one? Just tell me. What should be the idea to prove first one? Anybody? Anybody can tell me what is the idea to solve or to get the result? Abhijit? Abhijit Viskarma. Not here. Good. Achal Singh?
Yes, sir.
Yeah, Abhijit.
Yes, sir.
So my question is, what is the idea behind to prove this? We have to show that the inverse of A star is B equals to this. So what we have to do? What we have to do? Suppose if A and we have A inverse, suppose the inverse of A is A like this, denoted by A to the power minus 1. Okay, then what we write here? This should be how much?
A inverse equal to E.
E identity element. So
Yes.
this is the, we have to show that this. Okay, that means we have to show that A asterisk B. Okay,
Yes.
asterisk B asterisk, sorry, A asterisk B inverse, that is equal to what?
B star is A.
A asterisk B asterisk A inverse of A asterisk B, that is equal to E. Now
E.
you see, A is the, is this A asterisk B belongs to G?
Yes, sir.
Yes or no? Here.
Yes, sir. Closure.
By which property? Closure
Closure.
property.
Yes.
Okay. And now proceed this one. Use the associativity law, commutative law, not commutative because it is a group, not the abelian group. So use the associative law to prove that this star is, this is equal to E. If this condition is established, then we can say that this is equal to this. Okay.
Yes, sir.
Solve it.
Sir,
Yes.
sir, can you please explain once more?
Suppose A is any elements belongs to G. This implies A inverse also belongs to G because G is a group.
Yes, sir.
And A asterisk A inverse is also belongs to G by closure property. Okay. Now what we have to prove this? A belongs to G. AB belongs to G. This implies A asterisk B belongs to G. Okay. Now, if E is the identity of a group and A belongs to G, then A asterisk A inverse, that is equal to E. Okay. If it is a inverse, now we have A asterisk B, it is the element of G, and if this belongs to G, then its inverse also belongs to G.
Yes, sir. Got it.
Okay.
Yes.
Now you see here, just a minute. Here, leave this one. Erase this too. Important thing is to our question. Now, what is your question? Question is this: A asterisk B inverse is equal to this. So what we have to show that instead of this, we have to write it because this inverse, this is E, or if it is possible to show that A asterisk B asterisk B asterisk A star, this. If it is possible to show that this asterisk this, because you see here A B belongs to G, that means A inverse B inverse belongs to G. So this also belongs to G, this also belongs to G, this also belongs to G. Now the product of, that means composition of this and this with respect to this binary composition comes E. That means this element, then this element is equal to this element. Is it clear?
Yes, sir.
Okay. Find this. This is the fundamental to prove this.
Sir, please scroll a bit. Thank you, sir. It means when we will prove that A steric B steric A steric B inverse equal to, then we can proceed
We have
to
to
the.
prove this. Yes, we have to prove that this one. If you prove that this operated by this, okay, this composition this, sorry, asterisk this, that means this is the inverse of this. Okay, that means
Yes.
this can be written as A asterisk B inverse. This is equal to B inverse asterisk A inverse. Proceed it.
Can you show the second question?
Second question is, if H be a subgroup of G such that A square belongs to G for all A, then prove that H is a normal subgroup. How to prove this normal subgroup? H is a subgroup. Okay. Think about this.
Sir. So,
Hello. Hello.
The first question is done.
Question number 2. If you are facing problem in
Doing.
2, then go to the 3, 3, 4, 3, 4. These are easy. If A is the generator of a cyclic group G, then so that A inverse is also the generator. It is quite simple.
Yes, sir, doing.
sir.
Okay. Yes.
Sir, in second one, do we have to prove abelian group?
No, normal subgroup.
No, sir. Then
Oh.
ऐसे तो ये it is written only no that it is a subgroup of G तो abelian group का subgroup is normal subgroup only ना तो we can do that.
What?
Sir, abelian group का subgroup is normal subgroup ना.
Group of subgroup of abelian group is normal subgroup.
Yes sir.
Subgroup of a normal subgroup abelian. Simply prove that one. Whatever you are saying, that a subgroup of a abelian group is a normal subgroup. You are claiming this one. Try to prove that one first.
I am just thinking, sir.
No. If you know these theorems, then try to prove that one first.
Okay, sir, I'll try.
Or otherwise, what is so?
The normal subgroup.
Otherwise, what is the definition?
For
Otherwise,
yes,
you
A
so
subset,
A inverse.
H A subset, subgroup of N.
Actually, don't confuse with this coset and this abelian group. Okay.
Yes, sir.
So actually, you have to suppose if H is a subgroup, then this A. And this is to A. If this condition holds, then you can show that 2. If you're facing problem in 2, then leave it. Go to the 3 and 4. I will prove this true. Okay.
Yes.
Go to the question of the cyclic group. Okay. If A is the generator of a cyclic group G, then so that A inverse is also the generator of that cyclic group. Question number 3 is quite easy. If A is the generator of a cyclic group, then so that A inverse is also a cyclic group of G. What is the definition of cyclic group? What is the
Each
definition of a
element of G can be expressed in that form. Sorry, A to the power
Sir,
n.
A to the power A का power में we can do.
What is R? R? What is R?
Sir, where R is some integer.
Integers. Good. Now come to this. Suppose a generator Okay, A be the generator of, just a minute. Okay. So A is the, suppose A is the generator of a cyclic groups, then any element can be expressed in terms of A to the power R. Okay, and since A belongs to G, so A inverse also belongs to G. Okay, now A to
Yes.
the power R can be written as A to the power minus 1 to the power minus R, where minus R it is also an integer. So what you see, any element can be expressed in powers of A to the power minus 1, because R is an integer, so minus R is also an integer. Okay, so if A is the generator of G, then A inverse is also generator of this. Okay, now extra, suppose one thing, if I'm writing like so that every cyclic group is abelian, so that every cyclic group uh, so that
So,
is an yes.
so that this question, generator part. So if we somehow prove that A is equals to A inverse, so then can
A
to
is
say
equal
that
to
A inverse is
A equals
A
to A inverse.
inverse. Yes, sir.
A equals to A inverse. How? Suppose I'm giving you a question. Okay. Uh, suppose cyclic group. A equals to A inverse. How? That means
Sir, if
if
we multiply,
in a group, if no, if in a group each element is inverse of itself, then it is cyclic group. How you prove this one? For example, just simple. I'm giving you an example. Uh, example is, suppose we have a G is equal to 1 minus 1 I minus I. Okay, it is a group. It is a multiplicative group, finite group. Okay, so what is the identity element? Identity element is what? 1. So you see, what is the inverse? A multiplicative inverse is how much of this? If you multiplicative, that means minus 1 into minus 1, 1 itself. But I into I equals to how much? I into I, this is minus 1 into minus 1. It is 1. That's okay. I into I. If the inverse of I is I itself, then this would be minus 1. So it is not an identity. So I is not the inverse of itself. Similarly, this you can also see the minus I into minus I. This is also minus 1. Okay. But minus I into I, it is 1, or I into minus I. That means the inverse of I is minus I, and the inverse of minus I is I. That means whatever you claim that if every element is the inverse of itself, then it is a cyclic, then it is wrong, because it is a cyclic group. I is the cycle, similarly minus I is also the cycle of this. Is it?
Yes.
Yes, sir.
Okay. You can prove this one also. It is also a problem from the cyclic group. Uh, so that the every cyclic group is a abelian group. Every cyclic group is a abelian group. How can you prove this one? Every cyclic group is an abelian group. Hmm? I have solved this problem. I already solved this problem. You see the notes. So that every cyclic group is a abelian group.
So
And after
C
that, you prove this for.
G and then could be given in some power. So let two elements belongs to G, and then that two elements could be taken in powers of A to the power P
Yes.
or A to the power Q,
That's
that way.
okay. That means suppose the two elements, suppose S equals to A to the power R, and T is equal to, sorry, P, and T is equal to A to the power K, then ST equal to how much? AP plus Q, and it is AQ plus P, and this is A to the power K, A to the power K, and this is TS. Okay.
Yes, sir.
Okay, go to the question number 4. Question number 4, try to solve it.
Sir, 2 generators.
Sir, 3 and 5.
हाँ 3 and 5. 2.
What happened? Question number
Sir,
4.
3 and 5 are generators.
Hmm?
Sir, 3 and 5 are generators.
3 and 5 are
Yes, sir.
generators. How? 3 and 5 are generators. 1, 2, 3. 1, 2, 3, 4, 5, 6. Only this. Okay, and modulo 7. Multiplication modulo 7. It is cyclic. How you say that? Why not 1 and 2, 4 and 6? Hello? Why not? You are saying this 3 and 5. How? 3. You see, 3. You are saying the 3 because 3 to the power 1 is 3. We have to return in the powers of 2. 3 square, that can be written as what? 3 modulo 7, 3. So how much? 3 into 3, 9. That's divided by 7. That's give you the remainder 2. Okay? 3 cube. So how you write it? 3 modulo 7 and 3 modulo 7 and 3 modulo 7. That means 3 into 3 into 3, 27 divided by 7. How much you will get? What would be the remainder?
2, sir.
27 divided by 7. How much you will get?
6.
6, sir.
6. 3 to the power 4. So how much you will getting? 3, 4 times. So 27 into 3. So how much you will getting? 21, this is 81. Okay, divided by 7. How much you will get? 77. That means 4 you will get. 3 to the power 4, you will get 4. Similarly, 3 to the power 5, how much you will get? Into 3, so 3, 24. So divided by 7, what you will get? 7, 3, 33, or plus 5, it will come 5, and 3 to the power 6, that will come how much? Into 3, so 9, so 729, 7, and 1. You'll get 1 over here. Okay, so what you see? 1 can be expressed in terms of these, 2 in terms of these, 3. So you can write 1, 2, 3, 4, 5, 6 in terms of what? 1 is 3, and then 2 is divided by 3 square. 3 is for 3, sorry. 1 is 3 to the power 6. It is 3 to the power 1. 4 is 3 to the power 4, 3 to the power 5, and 3 to the power 3. So, yes, it's okay. 3 is the generator of this. And again, you say 5. Can you express this in terms of 1, 2, 3, 4, 5, 6? One of you told that 5 is the generator. Then tell me. 1 equals to 5 to the power how much?
0.
No, not the 5 to the 0, 0. No. It is 1, 2, 3. 1, 2, 3, 4. This should be the element of this. I will get 0. 5. That is 5. Okay, because modulo is 7. 5 is square. That is 5 modulo 7 and 5. So what? 5 by 25 and 7, 3. It will be 4. Okay. So it is 4 is denoted by 5 to the power 2. Okay. And this 5 cube. How much it is? 125 divided by 7. How much you'll get?
3.
So how much it is? 3. Okay. So 3 in place of 5 to the power 3. Take it. Okay. Well, you can check this one. Okay. So leave it next class. Okay. Everybody try the question number 2. Otherwise, I will solve it. Here you
Okay,
need
sir.
the concept of the coset. First you read coset, and next class we will discuss the cyclic permutation, even and odd permutations. These are important. Okay. So next class I will discuss that one also. Okay.
Okay, sir.